Welcome back, Focus Learners. Today, we're jumping right into something you probably interact with, dozens of times a day without even realizing it. We are talking about the invisible engines of the modern web. Those absolutely crucial advanced algorithms that process your digital actions. I mean, from the second you wake up and check your phone, all the way to your late-night streaming binges. We're stepping way beyond basic machine learning here to uncover the actual math that makes your digital world feel so incredibly personalized. Okay, let's dive into this explainer and see how it all works.
Just think about your daily routine for a second. You open up a search engine, right? And it just magically auto-completes your sentence. Or you search for a specific product, and boom, the exact link you need is sitting right there in the #1 spot. You fire up Netflix or Amazon, and it suggests a movie you have literally never heard of, but you end up absolutely loving it. So how does the internet seem to know exactly what you want before you even finish typing? It honestly feels like mind reading, doesn't it? But of course, it's not magic. It's math.
You see, basic machine learning is fantastic for straightforward stuff. But predicting complex human behavior? Yeah, that requires a totally different level of sophistication. To really wrap our heads around how the web works today, we need to metaphorically open up the black box. We're going to look at 4 highly advanced algorithms that handle all the crazy nuance of our preferences, our language, and our everyday choices. And to do that, we have a pretty clear roadmap. First, teaching machines to measure. Second, ranking your search results. Third, recommending your next binge. And finally, understanding words through context.
Okay, so part 1, teaching machines to measure, or customizing the ruler. Before a machine can recommend or rank absolutely anything, it first has to know how to calculate similarity. Now, traditionally, machines use something called Euclidean distance to figure out how similar 2 items are. It's kind of the standard metric. And sure, it's logical, but it's also completely arbitrary because it assumes every single feature of an item is equally important. But what if one feature matters way more than the others for your specific dataset? Well, that is exactly where custom metric learning comes in. Instead of forcing a one-size-fits-all ruler, the machine actually trains its metric from the data itself. It's kind of like putting on a pair of data glasses that instantly magnify the most important features and shrink down all the irrelevant ones.
And this brilliantly illustrates the actual math behind that custom metric. We can see how the standard distance is modified using a parameterizable matrix called A. By using a general diagonal matrix, different dimensions actually get different weights. So maybe dimension 2 is the most important one, right? Boom, it gets a higher value. But there are some pretty strict mathematical rules to be considered a true metric. To satisfy rules like non-negativity and the triangle inequality, this matrix A has to what mathematicians call positive semi-definite. Really, that's just a fancy mathematical way of making sure our custom ruler doesn't measure negative distances, because, well, that wouldn't make any sense in reality. We train this matrix by feeding the system pairs of items we know are similar and pairs we know are dissimilar, and it just naturally learns the optimal way to measure.
Moving on to part 2, ranking your search results, ordering the web.
So when you type a query into a search engine, thousands of pages match your words. How on earth does the machine decide the order? Let's trace how this builds through the evolution of search technology. Initially, algorithms used a pointwise approach. They evaluated every single document in total isolation and just gave it a score. But think about it, that completely ignores the context of the other pages. So we stepped up to pairwise. Here, the model takes pairs of documents and asks, okay, should document A be ranked higher than document B? Better, for sure, but still not perfect. Finally, we arrive at the absolute state-of-the-art, list-wise. With this approach, the algorithm doesn't just look at single pages or pairs. It actually optimizes the quality of the entire ranked list all at once. Which brings up a crucial question. How do we actually measure the quality of that entire list? Enter mean average precision, or MAP. This is literally the gold standard for search engines. Human judges actually sit down, examine search results, and label them as relevant or irrelevant. MAP combines all those human judgments to give the ranking a true overall quality score. State-of-the-art algorithms like LambdaMart are incredible because they use a technique called gradient boosting to optimize this MAP metric directly. They literally tweak their own sorting behavior to maximize the very human definition of a good search result.
All right, part 3, recommending your next binge, escaping this filter bubble.
Think about when you sit down on the couch to watch a streaming service. How does it actually know what you want to watch? Traditionally, there are 2 main ways to do this. Content-based filtering looks at what you've watched, let's say a bunch of sci-fi movies, and just recommends more sci-fi movies. The huge danger here is getting trapped in a filter bubble. It locks you in a loop of identical content, completely isolating you from anything new. So to escape that bubble, we use collaborative filtering. This method ignores the content of the movie entirely. Instead, it looks at other users. If you and another user both gave 5 stars to the exact same 10 movies, the system is going to recommend the 11th movie that user loved to you, even if it's a totally different genre. That right there is the secret to discovering that incredible movie you'd never even heard of. Now, what's really interesting about this concept is how the collaborative data is actually stored. Think of a massive grid, or matrix, where the rows are the users, the columns are the movies, and the numbers inside are the ratings. But here's the catch. In the real world, this matrix is incredibly huge, with millions of users and hundreds of thousands of movies. And because any single user only watches a tiny, tiny fraction of all those available movies, the matrix is mostly just empty zeros. It's what data scientists call extremely sparse data. Trying to pull meaningful recommendations from a giant grid of mostly empty space? Yeah, that is a massive mathematical headache.
So to solve this puzzle, engineers use algorithms like denoising autoencoders, or DAEs. Think of a DAE as a really brilliant detective. During training, the engineers intentionally take the few movies you actually rated and they erase them. They deliberately corrupt the data with noise. The neural network's entire job is to learn how to magically fill in those blanks and reconstruct your erased preferences. Once it becomes an absolute expert at reconstructing that erased data, it can look at your real, super sparse profile and accurately predict the movies you haven't even seen yet. It's essentially filling in the missing pieces of your taste profile.
And finally, part 4, understanding words through context, the guessing game.
When you're texting a friend or using a digital assistant, how does your phone actually understand the meaning of your words? Well, let's play a quick game. Listen to this sentence. I almost finished reading the blank on machine learning. What goes in the blank? You probably intuitively guessed book, article, or maybe paper, right? You knew exactly what fit there just by looking at the few words before and the few words after.
Believe it or not, that simple guessing game is the foundational secret to how machines learn language. The context words let you predict the central missing word. And the crazy thing is, it works the other way too. A central word can predict its surrounding context. This is the very heart of self-supervised learning. Nobody have to sit there and manually label data for the machine. The machine simply takes millions and millions of unlabeled text from the web, hides a central word, and trains itself over and over to guess what's missing using that surrounding window of context.
Now, that basic guessing game is scaled up massively using what's called a skipgram model. This fully connected neural network takes an input word and learns to predict all the surrounding context words. By forcing the network through this tight bottleneck in the middle, the embedding layer, the machine extracts dense mathematical representations of words. These are known as word embeddings, like the really famous word tvec. And because words like book and article share very similar contexts, their mathematical vectors end up being super similar inside the machine's brain. It's pretty amazing.
So, from custom metric learning adjusting our rulers, to list-wise ranking ordering our knowledge, collaborative filters breaking us out of bubbles, and self-supervised networks actually understanding our words, these algorithms truly form the invisible fabric of our digital lives. They take raw, chaotic data and turn it into the highly curated, deeply personalized web we rely on every single day. But as these neural networks just continue to evolve, learning from sparser data and vastly broader contexts, it leaves us with a really fascinating question. What happens to our digital world when these algorithms get so unbelievably smart that they understand our preferences, our queries, and our language even better than we understand them ourselves? Just a little something to think about the next time your phone finishes your sentence. Thanks for listening to this explainer, and keep learning.